Guys, okay, so it is Thursday, and I'm going to address both classes in this video, and then we're going to go over how to do the new type of stoichiometry problems. So just a couple of things. So I'm at home with my sick kiddo. She's got the stomach bug. And then I knew I was going to be out on Friday because I have a wedding to go to. So if we make it. So I will be out Thursday and Friday. So I'm going to give instructions in this video for all the things. And then you make sure that you do them appropriately, whether you're in the orange or the black days. So just because I've been out for 3 days and it's the end of the semester, I just wanted to talk about some of the grades. A lot of the stoichiometry problems, even though I'm having them due before the end of this week, like the problems you were working on yesterday and the problems you were supposed to turn in yesterday, those 11 problems and then the 10 problems from the next day, they are due before you leave for break, but their assignment due date isn't until the last 9 weeks. So that way, if anybody was absent, and this is only going to apply to those people that were absent, if anybody is absent the first couple of days that I was there and then obviously came back and I wasn't there, it's to help those people out. So just understand that the due dates are still what I'm saying. Already should have turned in a couple of sets of stoichiometry problems, and then we're going to be working on one today and tomorrow, or tomorrow, depending on what class you're in. And they are due before break. Or finish them if you don't finish them in class. Okay, so what you need to do is, and it doesn't matter whether you're going to, obviously, whether this is an orange or black class. So just to address both, orange people, you are going to watch a video, a full period video on how to do limiting reactant stoichiometry. It is very easy, and it is all the things you already know, all the stoichiometry you already know, just applying it now. And then you are going to work through the set of problems tomorrow during your double period. And then obviously the other class then will watch the notes for the first period, and then the second period you're going to start the problems and then finish them on Friday during your single period. So that's the agenda for the next 2 days. So whether you're orange or black, go ahead and open up the limiting reactant notes. And we're going to go through them now. So this should fill up the first period of class learning how to do these problems. All right. Got to get my calculator here and watch the time so we don't run over the period. All right. So hopefully this works for me. All right. So limiting reactant problems, and this is just to give you a basic idea of how they work, okay? To give you an overall view of what a limiting reactant is and what this type of stoichiometry is. This area of my house does not get internet very well. Okay, so limiting and excess reactants. So this is an example. I'm actually going to get rid of myself because we're going to take up the whole space. So here's an example of how to explain limiting reactants. So if I have 13 cookies and a half a gallon of ice cream, which is 10 large scoops, and I know this is out there, stick with me here. If you want to make an ice cream sandwich, which we all know ice cream sandwiches are made with 2 cookies on the outside edge and a scoop of ice cream in the middle. So if you want to make ice cream sandwiches with these materials that you have 13 cookies and you have 10 scoops of ice cream. So 1 scoop and 2 cookies makes a sandwich. The questions are, and this is exactly how they are in stoichiometry, how many sandwiches do we make? Which thing runs out first, the cookies or the ice cream? And then which one do we have left over of, and how many? So if you think about it, how many sandwiches can we make? Hopefully you guys would be able to figure this out if you were actually answering me in class. But obviously if it takes 2 cookies, that would make 6 sandwiches. And I made this an odd number. That doesn't work. Let's go 12. So say we have 12 cookies. Um, if we have 12 cookies and 10 large scoops, with 12 cookies, we can make 6 sandwiches. With 10 large scoops, we can make 10 sandwiches. However, our cookies are going to run out first. So how many sandwiches do we make? Of course, we make 6 sandwiches. We can't make 7 sandwiches. We don't have enough. We can't make 8 sandwiches. Which one runs out first? Obviously, the cookies run out first. Which do we have left over of? Well, we have scoops of ice cream left over. And how many do we have? If we only use 6 scoops for the 6 sandwiches, then we have 4 scoops left. And this is exactly what limiting reactant stoichiometry is. It is giving 2 amounts in a chemical reaction, and you have to figure out which one of them runs out first and which one do you have left over of. And sometimes you have to figure out how much leftover there is. Okay, so let's just define a couple things. What is limiting reactant? Limiting reactant is the reactant that runs out first. I want to point out too, just going to write this in up at the top. Sometimes the word reagent comes up instead of reactant. They mean the same thing. So please don't be confused if you see that on a worksheet. It means the same thing. So then the excess reactant, of course, is the reactant that does not run out first. It's the reactant that has some leftover after the reaction has been completed. We are actually going to come back up here and put the limiting reactant is also, it is the deciding factor for everything that is created in this chemical reaction. So this determines all the products made. And what I mean by all the products made is the amount of each product made is dictated solely by the limiting reactant. Because if the limiting reactant runs out first, just like the cookies and ice cream example, if we ran out of cookies, it doesn't matter how much ice cream we have, we're done making cookies. I mean, ice cream sandwiches. Confusing myself on my example. Okay, so I'm going to show you what to do. Okay, I'm going to show you an example problem, and then I'll have you work through a few other ones. So this is no different than any other stoichiometry problems we've done so far. You are to write and balance a chemical equation first. So please, if you need to pause the video and write and balance the chemical equation in your notes, please do so. We would be doing this in class, so write and balance the chemical equation of what's going on in this problem. So we have 23 grams of iron 2 chloride. Reacts with 41 grams of sodium phosphate. I'm not going to get caught up in the numbers yet. Remember, everything just needs to start with a balanced chemical equation. So the iron is going to combine with the phosphate. It stays as iron 3. So we have Fe3, PO4 plus, and then the Na and the Cl, of course, make sodium chloride. All right, then I'm going to balance. I need 3 irons over here. I need 2 phosphates here. And then I need 6 sodiums and 6 chlorines. So again, this is all stuff you know how to do. Just going through it faster. All right, so before, when we did stoichiometry problems, I would always have you write somewhere over, underneath, or above these things what is being produced, or what is given to you in the problem, and then what's the unknown with question marks. In this particular one, they give us 2 numbers. So we have 23 grams of iron 2 chloride. So there's 23 grams of this, and then there's 41 grams of sodium phosphate, 41 grams of this. Now, they give us 2 numbers. So in this particular problem, it does matter what one you start with, because it's asking what's the limiting reagent, the limiting reactant in this problem. So one of these 2 things is going to run out first. It is not always going to be the smaller number. So don't just look at it and be like, well, there's less of this, it might run out first. That's not always the case. Remember, stoichiometry produces all kinds of different things because of our mole ratios, our balanced chemical equation gives us those different numbers. So what we have to do, and I'm going to read ahead because sometimes the problem wants me to do something else. So what is the limiting reagent? So they want to know of sodium phosphate and iron 2 chloride, which one runs out first, and then what is the excess reagent. So they're simply asking, and the unique thing about these problems, unlike problems before, there's usually multiple questions to the problem, and they're not always the same. So this problem is just asking you to identify which is the limiting reactant and which is the excess reactant. It's not asking you to figure out how much leftover there is like we did before. So what we do is we start two bridges. It seems like a lot, I realize. We have to do two separate bridges, each starting with the number that's given to us. So we'll start one bridge with FeCl2, and we'll start our other bridge. I'm going to make it a long one. That's why I said I needed all my space, and I don't need my head shot in there. And then 41 grams of Na3PO4. All right. Now, what we do is we build to the same product. So we have, of course, iron 2 phosphate, and we have sodium chloride. If it does not specify in the problem which product you build your bridge to, sometimes the problem says how much sodium chloride is produced. So you would just go to the sodium chloride. If you have a choice and it does not say specifically which product it wants you to build the bridge to, I always just pick the easier one that has less things to add up. Like the sodium chloride, of course, has just sodium and chlorine. So, and I did not think about the fact that I don't have a periodic table to look at the molar masses. Okay, that's okay. So we are going to take and we're going to build a bridge. So basically, I'm realizing that right now. We're going to build a bridge going from 23 grams of iron 2 chloride to grams of sodium chloride. And then our second bridge is going to start with 41 grams of sodium phosphate and end with sodium chloride, grams of sodium chloride. So both of our bridges will have some answer that is grams of NaCl. And then this one will also be grams of NaCl. Okay? So we're shooting for the same goal in these. So we just set up our normal bridges like we know how to do. We can go from grams to moles. You know this. This is just what we learned before. Then we go from moles of one thing to moles of the other thing, whatever we're shooting for, which in this particular case we chose NaCl, and then moles of NaCl to grams. Okay, so there's our first bridge. Remember, one always goes with moles when there's grams in the other spot. In the center section where we have moles over moles, we look at our balanced equation. So we have 6 moles of NaCl, and we have 3 moles of FeCl2. And then I'm going to ask Siri, hopefully my phone doesn't die on me, what is the molar mass of iron 2 chloride? So this is 125.87. And again, you would just be doing this on your own with your periodic table. Sodium chloride is 58.44. It seems like I made that up, but I really think that's right. So we're going to go with it. If it's wrong, fix it in your thing. Na3PO4, 2 moles. So again, we're going to set up our second bridge. Same way. We're getting rid of, I'm sorry, this is so messy, guys. And then we would go from moles of Na3PO4 to moles of sodium chloride, and then moles to grams. NaCl to grams of NaCl. Of course, this gets a 1 and this gets 1. In our mole section of the bridge, we look at our balanced equation. Of course, we have 6 moles of NaCl, and we have up here 2 moles of Na3PO4. And then what is the molar mass of sodium phosphate? 163.94. And then I'm sticking with 58.44. You know what? I'm going to check myself. What is the molar mass of sodium chloride? I think they're lying. 57.95 is what it says, but I'm sticking with 58.44. 23 plus 35.45. 23 plus 35.45 is 58.45, but I think this is 22.99. Okay. Anyways, my thought process. Okay, so rounding to the correct number of sig figs. I'm going to go to my calculator here. I'm going to multiply across the top, so you can go ahead and please make sure that you're working these out as I'm working them out, just like we were in class doing it. I don't know if you guys have noticed. I mean, I don't know if you were doing this in problems before. Like in the center section of the bridge, if I have 6 over 3, I'm going to reduce that. So I only have to multiply by 2. Same down here. 6 over 2 is 3 over 1. Terrible 3. So I'm going to fix that. Times 2 divided by, no, times 58.44. So on the top, I get 21.3, well, with the correct number of sig figs, 21. And then on the bottom one, divided by 163.94 times 3. I guess I could have kept my face on here. Is it awkward that my face is not on here? Can I get it back? Embed webcam. There I am. Okay. There I am again. I know it's in the way, but I can move me up here. It's kind of weird if I'm not in the video. Okay. I mean, maybe it's not. Whatever. Maybe you don't even care. Times 3 times 58.11. 58.44. Okay, so with correct number of sig figs, we get 44 grams. Now, here's the part we have to analyze what this means. What is this telling us? Well, this is telling us that one of these two things produces less sodium chloride than the other. So if I use up all 23 grams of FeCl2, all the sodium chloride that I'm going to make is 21 grams. If I use up all the 41 grams of the Na3PO4, I'm going to be able to produce 44 grams of NaCl. So just like the cookies and the ice cream situation, according to my cookies, I can make 6 ice cream sandwiches because I need 2 per sandwich. But according to my ice cream, I could make 10. Which one limits the amount of sandwiches I get out? The one that produces less of the product. So down here with this problem, whichever one of these, and that's why we went to the same thing, because we want to compare the same value. So whichever one gives you a smaller number, then we go back to the beginning of that bridge. It's not correct to say that the limiting reactant is 21 grams of sodium chloride. That's not a reactant at all, actually. That's a product. So what you have to do is you have to go back to the beginning of the bridge. I always just box it, and then I write above it limiting. I do this even if they're not asking, just because it helps me keep them straight. And then the question is also asking, what is the excess reagent? Well, we're not going to use all 41 grams of, just like we didn't use all 10 scoops of ice cream. This is the one that's in excess. So when you answer a question like what is the limiting reagent or the limiting reactant, you should be identifying one of the two reactants. If I answered it with a product, then I wouldn't be answering the question. So what's the limiting reactant? The limiting reactant is FeCl2. What is the excess reactant? The excess reactant is Na3PO4. And that's all I need to do for that. That's all they're asking. They're not asking us how much excess. They're not asking us how much product is formed. They're just asking what's the limiting and excess. So again, every problem is a little different. That problem is asking us to identify the limiting and excess. Let's see what, oh, no, they're not. They're going on. Okay, if 23 grams of, same problem, what is the limiting reagent? What is the excess reagent? All right, so here we go. Here's the next one. How much excess is there? I just lied to you. It does ask you that. And I want you to see all the different types of problems. So if we're not going to use up all 41 grams of sodium phosphate, not all 41 is going to be used up. So we're going to use up some of it in the reaction, Not all of it though, and there's going to be some left over, just like up here. I keep referring back to this because I think it makes sense. So we're not going to use all 10 scoops of ice cream to make our 6 sandwiches. We're going to use only 6 scoops, leaving us with 4 scoops left over. Okay, so same thing down here when you are trying to figure out how much excess there is. You have to build a bridge that goes from limiting to excess. So I'm actually going to put that here. When the question asks how much excess is there, that's when you build a bridge. Let's type it in, because typing would probably be way nicer writing than me trying to scribble it. Okay, so when we are asked about how much excess there is, we build a bridge starting with the limiting and going to the excess. Okay, we're just going to go smaller with this because I don't want it down. All right, so basically that means, since I identified that in the last problem, we have our limiting reactant, which is the FeCl2. That's our limiting reactant. We know what that is. So we're going to go down here. We're going to build a bridge that starts with the limiting reactant. 23 grams of FeCl2. And we're going to go to the excess reactant. Okay, so I'm going to go from, and just to identify what I'm doing here before I do it, I'm going to go from FeCl2, grams of FeCl2, to grams of the excess reactant, which in this particular case is the Na3PO4. So we're going from grams of FeCl2 to grams of Na3PO4. Okay, so let's get rid of grams of FeCl2, go to moles, and then once I'm at moles of FeCl2, I can go from that to moles of anything else, which in this particular case, I'm going to my excess reactant, Na3PO4, and then I don't want to stop there. I want to go from moles of Na3PO4 to grams of Na3PO4. Okay. So the nice thing about this second bridge, if they ask this, is that you've already calculated all the molar masses. Obviously, we didn't calculate them. We just asked our phone. But so we have 1 and 1. 1 here, 1 here. I'm going to go to my balanced equation. Na3PO4 is a 2, and the FeCl is a 3. So I go to 2 there and a 3 there. And then I'm going to go up to my other bridge. FeCl2 is 125.87, so that goes right here, 125.87. And then the Na3PO4 is 163.94, so I'm just using my values from before, 163.94. Don't reinvent the wheel and do it again, just use what you have. Okay, so multiplying across the top. All right, 23 divided by 125.87. Again, please be doing these while I'm doing them. I realize it's easy to just sit here and watch me do them, but 163.94. And then with the correct number of sig figs, we get an answer of 20 with a decimal point. Okay, so what does that mean? That is not the answer, right? Even though our grams of FeCl2 cancel, moles of Na3PO4 cancel, and we're left with grams of Na3PO4. Now, what this answer gives us is how much of the excess reactant is used up, not how much is left over. If I had 41 grams of it to begin with, and in this reaction 20 grams is used up, then how much is left over? Of course, you would subtract them. So 41 grams, what we had to start with, of Na3PO4 minus the amount of grams that were used when all of the limiting reactant was reacted is 20 grams of Na3PO4. You should be subtracting two numbers with the same units and the same label, and you end up with 21 grams of Na3PO4 left over. Da, 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 da. That's all to get to the answer. To the second question, which was, how much excess is there? Obviously, the cookies and the ice cream example is really simple and straightforward, but if you keep going back to what that example, hopefully it will help you think through these. We're going to be given two things that mix together to make some product. And we need to figure out which one runs out first. And once we figure out which one runs out first, that dictates everything that goes on in the reaction. That limiting reactant, in this case the FeCl2, is what dictates everything that's made. So with that said, the last question that you might be asked. So I'm giving you all the options for questions. Not every question that you ever come across with these limiting problems has all of these questions in it. Sometimes I just ask you what's the limiting and excess, and that's it. And all you have to do is that first problem that I did. Sometimes I ask you how much excess is there, or sometimes I would ask you how much sodium chloride can be formed. So we kind of already answered that back here. How much sodium chloride can be formed? So we built both of our bridges to sodium chloride, right? We built just because it was the lesser one. Now, if you would so happen to choose the one that was not lesser, like one that was smaller and you had to add less things up, and they asked for the other one in their final question, then you'd have to go back and do it again. That's why it pays off to look ahead in the question and see if they're asking about something specific. So what they're asking in this question is, how much sodium chloride can be formed? So we have 21 grams of sodium chloride and 44 grams of sodium chloride. So which one is the right amount of sodium chloride that is formed? So think about what that question is asking. Think about what we talked about. Which thing in this equation dictates all of what happens in this reaction? Well, of course, that's our limiting reactant. So if I know that the FeCl2 runs out first, the maximum amount of sodium chloride that can ever be produced is 21 grams of sodium chloride. So again, I already answered this question before, but I would just build a bridge that would look very similar to the one that is up there. 21 grams is the most amount of sodium chloride that can be produced. And why is that? Because FeCl2 will run out first because it's the limiting reactant. We never ever get to 44 grams of sodium chloride. We're never going to be able to produce that much because our iron 2 chloride runs out first. So once you've figured out which one's the limiting reactant, that then dictates all the products that are formed. So if the last question asked how much iron 2 phosphate is formed, you would have to build a bridge starting with your limiting reactant and going to that particular product, just like we did with the sodium chloride. It doesn't matter what the excess reactant does or how much of that product is formed from the excess reactant. It only matters starting with the limiting reactant. I hope that makes sense. I know it's a lot. It's just taking what we already know. You know how to do these problems already. You practiced them a whole bunch yesterday. It's just taking them and applying them to a example problem where you're given two reactants in uneven numbers that are not perfectly set up to react and be completely used up, both of them to the gram, to the microgram. Instead, you're given one amount that runs out first and another amount in excess, and you have to figure out which is which. So let's do another problem. Example 2. So I have multiple examples here. I'm not sure that we're going to get to all of them with the time frame because we're half hour in. Okay, so again, every problem starts with a balanced chemical equation. So, of course, we have 4.95 grams of ethylene, C2H4, are combusted. So we know combustion reactions look like this. We have C2H4. Combustion reactions are a hydrocarbon or carbohydrate that's combined with oxygen to make carbon dioxide and water. I hope at this point you know. And then we're going to balance it. So I'm going to put a 2 here to make that 4, and I'm going to put a 2 here to make that 2, and then I'm going to count up 4, 5, 6, and I'm going to put a 3 there. Okay. So then I go back to my problem. I identify my numbers. I put them where they go. So I have 4.95 grams of the ethylene, 4.95 grams of this, reacts with 3.25 grams of oxygen, 3.25 grams of this. So again, we're trying to figure out which of these two things runs out first. In this particular problem, they're asking us what is the limiting reactant and how much excess reactant is left over. Okay, so they're asking us those two questions. They're not asking us what's the excess reactant, but obviously you have to identify that in order to answer the second question. So I'm going to do what I did before. I'm going to start two bridges with the two numbers that are given to us. We're given numbers in the problem. Start your bridges with those. 4.95 grams of, oh, that was terrible, C2H4. Now, this is a particular problem where this is it. So like if you move on to the next one, it's the next example. I'm not adding to this question. So this, all they're asking is what is limiting reactant and how much excess is there. They're not asking us for one of the products and how much is produced. So I know the molar mass of water already. I have that in my head. A lot of you probably do too. So I'm going to build it to that because I just know that one and I don't have to look it up. I'll have to look up ethylene though. C2H4. Again, set this up just like we would do. So basically what I'm doing is I'm starting two bridges. Sorry, I got ahead of myself. Starting two bridges with the two numbers that are given to us, 3.25 grams of oxygen. And I'm building them to the same product so that I can compare. So I'm choosing the product water, and I'm going to build it to grams of water. How many grams of water do each of these produce? So again, my final answer to help me identify which one runs out first is my final answer to these bridges is both going to be in grams of water, and then I'm going to compare those two values. Okay, so moles of, back to my first bridge here, C2H4. Now that I'm at moles, I can go from moles of C2H4 to moles of whatever else I want, and I chose water as my product to go to, and then moles of water to grams of water. All right, one goes with moles, one goes with moles. Look at my balanced equation for this. I have 2 on the top and 1 on the bottom. And then, of course, I know molar mass of water is 18.02, and the molar mass of ethylene. What is the molar mass of ethylene? 28.03. Although it was wrong with that one, so sorry if some of these are wrong. This is my knowledge app. Don't know if that's right or not. Okay, so going to my calculator. I guess I can set up my second bridge, whatever you want to do. 4.95 divided by 28.03 times 2 times 18.02. So I get in the first problem with the correct number of sig figs, 0.489. All right, so in the bottom one, I get rid of grams of oxygen and go to moles of oxygen. Now that I'm at moles of oxygen, I go moles to moles of the substance that I chose, which was the water, and then moles of water to grams of water. Again, 1 and 18.02. Oops. 1 goes over here, and then, of course, oxygen's molar mass is 32.00, 16 times 2. And then my H2O is a 2 in my balanced equation, and my oxygen is a 3. So 3.25. I'm just assuming I'm not making mistakes. If I make a mistake, guys, and you find it, just correct it. I mean, you can't correct it to my face, but... Okay, and the top one, oh, that seems drastically different. Maybe I did do something wrong. Ugh. As I say that, I see I have a decimal point in the top one. Okay, let's just fix this one first. 11.0. You're probably yelling at me through the thing. 4, or maybe you didn't even notice. You're just trusting my work. Divided by 28.03 times 2 times 18.02. Okay, 6.36. Is this supposed to be this top one? 6.36. I had put a decimal in before the one value, which did not make sense at all. I don't know why it didn't say error. Okay, so now that I have my two answers, I can answer the question that they're asking. What is the limiting reactant? And then let's just start with that. So when I look at my two answers, I know that this much ethylene will produce 6.36 grams of water. I know that this much oxygen will produce 11 grams of water. Which of these two things, the ethylene or the oxygen, is my limiting reactant? Remember, when we're thinking of this, whichever one of these two things is a smaller value, comparing two things that are the same, grams of water, whichever one is a smaller value, that is telling us what the limiting reactant is. However, 6.36 grams of water is not the answer. We go back to the beginning of our bridge. We box that reactant because it's asking for a limiting reactant, and we label it limiting. Now, even though they don't ask this, I'm going to box oxygen and put excess. Because then they ask us how much excess reactant is left. Now I'm totally out of room here. How much excess reactant is left? So when we're trying to figure out how much excess is left, go and think about what that means. So 3.25 grams of oxygen, that's the excess reactant. Not all 3.25 grams is going to be used up. All of the ethylene is going to be used up. All 4.95 grams of ethylene will be used up, but there will be some leftover in this 3.25 grams of oxygen. Well, how much leftover? Well, we have to figure out how much is used. So remember, back here, what did we say? When we are trying to figure out how much excess, we build a bridge starting with the limiting and going to the excess. So that's why I label both of those things. Starting with the limiting. So I'm going to start it with, to answer this question, I'm going to start it with ethylene, grams of C2H4. And I'm going to build it to the excess reactant, which is grams of O2. Always go back to that slide before. So I'm going to build a bridge going from grams of ethylene to grams of oxygen. I'm going to put it up here. So we're going to squeeze it in. So how much ethylene do I have? 4.95 grams of C2H4. Okay, grams of C2H4 goes in the bottom. Moles of C2H4 goes on the top. Now that I'm at moles, I can go from moles of C2H4 to moles of, and remember, here's what I'm shooting for over here, grams of oxygen. So I have to go to moles of oxygen first, and then I go from moles of O2 to grams of O2. Now remember, this bridge is nice because we've already figured out all the molar masses of things. First, and I jump around on these, I realize that. In the center section here, I have 3 moles of O2 according to my balanced equation. C2H4, I only have 1 mole of that. We always put 1 in the slot that has grams over moles, moles over grams, and grams over moles. And then the molar mass of C2H4, we already calculated down here in our other bridge. We didn't calculate it, we just looked it up. 28.03. And oxygen, of course, we know is 32.00. Okay. Now, a way for you to know whether you did this problem right or not is if you get an answer of grams of oxygen here, and it is bigger than 3.25, you did something wrong. It's actually pretty foolproof. If you get the answer to this bridge and it is bigger than 3.25, the amount of oxygen you have to begin with, that you know you're not going to use up all of, you did something wrong. So it's a way to check to see if you actually did things right. So 4.95 divided by 28.03 times 3 times 32. So we get, with the correct number of sig figs, there's all these fun sig fig things, 17.0. Look what I just said. 4.95 divided by 28.03 times 3 times 32. What did I do wrong, guys? And see, I'm glad I just talked about that. Because clearly I screwed up that problem. See? 28 point and 32. See, and this is something we would be doing in class, sitting here thinking about what in the world we did wrong. We definitely aren't going to use up 17 grams. Maybe I calculated the excess wrong. Let's go back. You probably already know. You probably already know what I did wrong. And I hope you do. Times 18.02. 6.36. Okay. 3.25 divided by 32. Oh, maybe I didn't do that right. Divided by 3 times 18.02 equals. We didn't have the right thing. Did you catch my mistake? This is actually 1.22. See? You would have figured out that you didn't do the problem right if you did it the way I did it. Okay, so we totally labeled these wrong. Okay, so we just figured this out differently. Our limiting reactant is our oxygen, not our. So let's go back here and erase this. This is not right. This is not right. So we didn't even answer that question right. This is the excess, and this is the limiting. All right, so when we go up here, we're going to reverse this bridge. I wonder if I can reverse it with, no, I can't reverse it without doing it all over again. See, this is a learning moment. Right, guys? Maybe you're judging me. It's okay if you are. Okay, so we did the bridge right. We just didn't have the thing set up right. Okay, so we go from limiting to excess. So we're actually going to go from grams of O2 to grams of C2H4. I believe the bell's probably ringing. But come back. Yep, I'm sure it did. Come back and see me again. If you need to stop the video and start it again tomorrow, I would say do that. I should have said that before because some of you have already left. Okay. So we start with our 3.25 grams of oxygen. 3.25 grams of oxygen. And we build it to grams of ethylene. So O2, moles of O2. Then we go from moles of O2 to moles of C2H4. And then we go from moles of C2H4 to grams of C2H4. All right, let's see if we can get the right answer now. We have a 1 here, a 3 here, 1, 1, and then we have 4.9, nope, not 4.95, 28.03, 28.03, sorry, it's kind of a mess, and then 32. All right, of course, you know that's supposed to be 32.00. 3.25 divided by 32 divided by 3 times 28.03. Okay, so let's just say what we said before. If you end up with an answer of grams of C2H4 that is larger than 4.95, you did something wrong. Now this is right. Okay, so we have 0.949. 0.949. Wonder how many mistakes I made earlier. Now, that is not the answer, right? This is not the answer to the question, how much excess? This is just how much is used up in the reaction. This is how much is used up. But remember, we had 4.95 to start with. So to get your actual answer, you take how much you had to start with, 4.95 grams of C2H4, and subtract from it 0.949, how much was used up in the reaction, to figure out how much is left over. So 4.95 minus 0.949. So we have 4.00 grams of excess C2H4. That's a lot of excess. We barely used any at all. Okay? That answers the question. If you need a third example, you can go ahead and work through this as a third example, but you're going to get practice in a little bit. Okay, so hopefully, if you don't have a double period, you picked up the second day where you left off. I forget which class is which, but you know who you are. So now that you know how to do the problems, you are going to work through 10 problems just like we did before of limiting and excess problems. So I'm actually going to work through just one of them with you, and then I'll let you go. You have 2 periods to work on this. So you may have a period on Thursday and one period on Friday to work on these 10 problems, or you may have 2 periods on Friday to work on them. And hopefully you just pop back into the video to see what we were supposed to do. So, all right, so if you go back to the schedule and you open up the limiting reactant practice, please do this work on a separate sheet of notebook paper. So I'm going to be able to write on this. Yes, hopefully. Oh, yes, because it's a Cami. Okay. So, again, when we're doing these problems, all of them start with a balanced chemical equation. And I'll tell you right now, use your activity, series, and solubility rules because they matter. And if you don't write and balance the equation to begin with, it's going to be tricky. And every question asks something a little different. So don't just assume all of them are asking all the things that we were asking before. So this first question says, identify the limiting reactant when 4.68 grams of solid iron reacts with 2.88 grams of solid sulfur. So I'm going to pop down here. I'm going to write and balance an equation for solid iron, not in Brinkelhoff, reacting with solid sulfur. And I may not know because I don't have my big periodic table to look at it. What this is. Maybe Siri knows. What is the common charge for iron? Okay, bear with me for a minute. You could probably pop onto your periodic table really quick and see what the common charge is. I don't know if it's 2 or 3. Flynn periodic table. Oh. Don't fail me now, Flynn periodic table. That's ridiculous. No, I'm not going to be able to see that. So anyways, you know, we're not going to get this right. Sorry, guys. If I was in class and prepared, I would have what this is. That's not going to show it to us. Okay. Common charge of iron. Everything can be found on the internet. What is the most common charge of iron? Two plus and three plus. Yes, I know that. Which one's bold? We're going to go with 2. I hope that's right. I think it is. Seems right. Yeah, because I think we did this one in our problems before. Okay. Sorry that took so long because I know that you could look at your big periodic table and find it right away. All right, 4.68 grams of iron. 4.68 grams of iron. If you don't need this help, just stop and go do the problems. If you totally understand them, go do your thing. Okay? This is what we'd be doing in class. I'd be working with some people, and some people would just be off on a roll. So go do the problems. You got 2 periods to work on. Either Thursday and 1 period Friday, or 2 periods on Friday. Either way. 2.8 grams of solid sulfur. 2.8, is it 8.8? Yeah. Okay. So I only have one product to build to this time. The question is only asking me identify the limiting reactant, nothing else. So that's actually a really easy one. So I'm going to start one bridge with 4.68 grams of Fe, build a bridge. And the other bridge I'm going to start with 2.88 grams of S8, 2.88 grams of S8, build a bridge. Now, when you do these, remember you would normally just choose a product, but in this particular case, we only have one product, so I'm just going to go to grams of that one product. Again, assuming I have that right. If I don't, you fix it, okay? Okay, so grams of Fe to moles of Fe. Moles of Fe to moles of whatever else we want, which is our FeS. And moles of FeS to grams of FeS. Okay, so 1 and 1. I'm going to go fast through this because I did this before. If you need more. Oh, no, that's not right. Oh, yes, it is. 8 with this, 8 with the iron. So again, I'm just going to reduce that down to 1 and 1. Less typing. Iron, I feel like, is 55.88, 58.33. What is the molar mass of iron? 55.85. I don't think I said that. 55.85. And then what is the mass of sulfur? 32.06. So 32.06 plus 55.85 gives us 87.91. All right, and my other one, sulfur, 32.06 times 8. So I'm going to calculate this. Grams of S8 is 256.48. 256.48 over above 1 mole of S8. Then I have 1 mole of S8. S8 and 8 moles of FeS and 1 mole of FeS and 87.91 grams of FeS. Okay, so I'm doing my math, hopefully right. 4.68 divided by 55.85 times 87.91. 7.37. You should be putting this all on sheets of paper. So 7.37 grams of FeS, because you're going to turn in the sheet of notebook paper. So hopefully you're working this out with me. 2.88, or you're just working out on your own, which in that case you wouldn't be watching this. 256.48 times 8 times 87.91 with 3 sig figs. 7.90. This is actually really close. 7.90 grams of FeS. And the question asks us, what is the limiting reactant? So which of these two reactants runs out first, the iron or the sulfur? Well, the one that produces less product, we go back, and is the one that is the limiting reactant. So the iron is limiting. If they were asking the excess, of course, then we would say the sulfur. So be very careful as you work through these. Read what they're asking for. They may be specifying a certain product that they want you to calculate for. They may be just asking, like what that one did, identify the reactant. Again, I encourage you to use your activity series and solubility rules. So when you finish these, please make sure you turn them into the box. Like I said, you have, I think orange people have 2 days on Friday. 2 periods on Friday, and then black, you're going to start it on Thursday and finish on Friday. So, okay, work through those 10 problems. Okay, have a good spring break, guys.